you ever wondered how wind instruments like the saxophone, clarinet, or the flute produce their beautiful sounds? Or what makes one earthquake more dangerous than another? Today we're going to explore these using the idea of resonant frequencies. Resonant frequency is the frequency at which an object naturally oscillates or vibrates. And if you were to add another source that emits this exact same frequency, the vibrations become more prominent. Here is a short video that can help you understand resonance a little bit more.
On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
We are now going to simulate the behavior of the air particles inside the tube when someone blows into one. The blue dots represent those air particles, and as you can see, they are being displaced across the tube. If you were to plot the displacement of those particles as a function of the position along the tube, the moving red line highlights this behavior over time. The regions where the air particles do not move at all are what we call nodes, and conversely, the regions where we see the particles being displaced the most are what we call antinodes. Together, the graph that we end up is a standing wave. In order for the standing wave to be present inside the tube, a particular condition needs to be met, and it relates the length of the tube and the wavelength of the wave. This condition is that half of the wavelength must fit inside the length of the tube. In mathematical terms, L, the length of the tube, is equal to lambda, the wavelength, over 2. Using the relation between the speed of sound and its frequency and wavelength, that is, V is equal to frequency times wavelength, we can determine the frequency for this particular setup shown. This is what we call the fundamental resonant frequency. The fundamental resonant frequency is the lowest frequency at which the object displays resonance. You can also hear different resonant frequencies, and we call these harmonic frequencies, and they are integer multiples of the fundamental resonant frequency. Now that we have seen what happens to the air particles inside a tube that undergoes resonance, let's try to measure their frequencies. Here I have two pipes. These are made from the same material, they both have holes on both ends, and the only thing that is different is their lengths. We are going to measure one of its resonant frequencies using phyphox, a free app, and its audio spectrum feature. It will generate a graph where the y-axis represents how much a particular frequency is being detected, higher meaning more of it is being heard, and the x-axis represents the range of frequencies. What I will do to produce the actual sound is to blow into the pipes perpendicular to it. So not directly into the pipe, but just above the hole on one end. phyphox will then use this to produce the graph as mentioned before. Let's start with the longer pipe. For this longer pipe, we can see that the high speed corresponds to 632.81 Hz. Recall that this frequency can either be its fundamental frequency or one of its harmonic frequencies. Now, let's try the shorter one and see if we get a lower or higher or perhaps the same resonant frequency. Make a prediction if you like. For this shorter pipe, we can see that the high speed corresponds to 984.37 Hz. This is higher than the longer one, and you could hear that this one had a higher pitch as well. We've tried a long pipe. We've also tried a short pipe. We're now going to try the same thing, but with a pipe that is in between the long and the short pipe. We established a relationship between the length of the pipe and the resonant frequencies. Based on this relationship, what do you think the resonant frequency of this pipe is going to be? Pause the video for a few seconds and come up with your answer. Now, let's put it to the test. For this pipe, we can see that the highest peak corresponds to 820.31 Hz. This is right in between the resonant frequencies of the longer and shorter pipe. This is because the length of this pipe was in between the longer and the shorter pipe, and we knew that longer pipes produced a lower frequency and shorter pipes produced a higher frequency. This brings us to the end. Let's briefly recap the things that we learned. We learned that the resonant frequency is the frequency at which an object naturally vibrates or oscillates. We went ahead and simulated what happens to the air particles inside an open tube. In accordance, we defined the terms standing waves, fundamental and harmonic resonant frequencies. Lastly, we have concluded that varying the length of the pipe also varied their resonant frequencies, which can be their fundamental or harmonic frequencies. I hope that you learned a bit more about resonance and how we can experience it in the world around us. Thank you.